This discussion will focus on the first section of material. We will start with Unit 1, which is an introduction to the field of statistics, and we talk a good bit about data collection. There are 3 sections in this unit. The first section being an introduction to statistics, which is essentially an introduction to lots of the terminology that we use, the common terminology, how we classify variables, how we classify different kinds of studies. So some of the basics that we need to know for upcoming material. That will be what we focus on. What you'll notice is that the lecture videos go along with the notes, so it's very important that you read the notes before you watch the videos. The videos really focus on example type problems and reference back to material that you should have read in the notes. So it's very important to read the notes first. I always like to start with just talking about some examples of statistics and some things that you tend to see. The nice thing about statistics as compared to lots of mathematical kinds of courses is statistics is something that you see in your daily life, whether in the newspaper, on the news, or in your job. Any kind of professional career is going to include some sort of statistical analysis where you see things reported, whether it's something simple as a percentage or averages, things that they use to help them make decisions as a business. So it is a very applicable to many different areas. You'll see it in business, medicine, sports, education, politics. We're just going to pick a couple examples so we can start talking about some of the things to look for when you see a statistics. And one of the main things we'll talk about is how we distinguish between the 2 branches of statistics, descriptive statistics as compared to inferential statistics. Our first example we're going to look at is a sports example. Let's just suppose that we look at the free throw percentage for Anthony Davis. If you look at free throw percentage for a basketball player in the newspaper, one of the things that we always look for whenever we look at statistics is whether or not there's error involved in that statistic. And that's a key sign as to whether we're just describing the information or whether we're actually trying to make some sort of inference, because descriptive statistics have no error and inferential statistics include error because of the estimation. So if you think about something like Anthony Davis's free throw percentage, just think about, is there any error involved in that statistic? And of course, one of the reasons why we know there's not is when you look in the newspaper, it's not going to report any kind of error. But beyond that, it's important to note why there is no error. If you think about his free throw percentage, basically what they do is they take over a certain period of time, they know exactly how many shots he's taken and exactly how many shots he's made. If they just take the number he's made divided by the number he's taken, that gives them a percentage. And the reason why there's no error in that statistic is because they have all of the data. They have everything they need in order to calculate that. They're just simply summarizing his performance over that period of time. And that's what a descriptive statistic is. It's just summarizing the data that we have, whatever that might be. If we compare that to something that is inferential, something like the president's approval rating, you'll notice when you look at the president's approval rating, if you look that up, you'll notice that with the president's approval rating, they do report error. They typically report what's called margin of error. We also call that error tolerance in statistics. But that idea of margin of error is something that you will commonly see reported with some statistics and not with others. So it's an important thing to notice. So why is the president's approval rating, why does it have error? And it comes from the fact that when they collect data, they don't really ask everyone whether or not they approve of the president's performance. So basically, they don't have all the data. Unlike Anthony Davis's free throw percentage, where they're just summarizing what they have. In the case like the president's approval rating, they're not going to ask every single person what their opinion is of the president. So what they do instead is they take what we call a sample. They take a smaller group from that population, and then they use that to estimate the population. So they might take 2,000 people and use those 2,000 people to make an estimate of what would happen with the population. So where does that error come from? Let's talk a little bit about that. It comes from the basic idea that we're not collecting data from everyone. But let's talk about that a little more. If you think about the president's approval rating and you look at it, and I'm just going to pick some numbers, just suppose the president's approval rating is 40%. If there's a margin of error of 3%, then that tells you that it's basically 40%, which is the value they got from the sample, plus or minus that 3% of error, which tells us that we are confident that the president's actual approval rating is between 37 and 43%. We just take the 40% plus or minus the 3%. So that 3% comes from the fact that we did not collect data from everyone, but it's a little more involved than that. And by the end of the semester, you'll understand this much better. But essentially, that 3% comes from the idea of probability. We need to take our sample, and when we take our sample, we take it in such a way that we're able to calculate probability. And through those calculations, we're able to figure out how much error I would expect in this statistic, in this 40%. And with a certain level of confidence, how much error will there be? So we know that that error, usually when you look at confidence levels in the newspaper, it's usually 95%. So we basically know we're 95% confident that the president's approval rating is between 37 and 43%. Do notice with inferential statistics is there is always a chance that you're not correct. We're only 95% confident, which is very confident, but there is a 5% chance that we're wrong, and that's something to be aware of. Anytime you do inferential statistics, there's always that chance of making a mistake, and that's something that we have to think about as we cover material. So we could go through lots of different examples, but I just wanted to give you a couple and just talk a little bit about the difference between descriptive and inferential statistics. In statistics, we really study four main things. We study how we collect data, how we organize that data, how we analyze it, and then how we interpret that information. So what we really start with in here is we start with the idea of just some basic terminology and how we collect data. That's really a lot of what we talk about in this first unit. Collecting data is one of the most important parts of any kind of statistical process, because if you don't collect the data in a certain way, then as I mentioned before, in terms of how we estimate things with probability, if you don't collect the data in a certain way, then you're unable to calculate that probability. And being able to calculate that probability is key to knowing how much error we have in our estimates. I used to do some statistical consulting, and one of the common mistakes that people will make is they'll collect their data, and then they'll come and ask me, well, this is what I want to do with my data. And about half the time you end up telling them, well, you can't do that because you didn't properly collect your data. So the data collection process is an overlooked step lots of times. People think they can just take any kind of data and do what they want with it, and that's really not the way it works. The mathematical process assumes that you collected your data in a certain way. So that's kind of what we start with in here. We don't do a lot with organization of data. These days, that is not a big issue with software advances. So software is usually used to organize data, and we don't do a lot with software in Stat 210. After this first unit, then we get into really what we ultimately want to do with our statistics, which is analyze and interpret. And that's what the bulk of the class is once we have our data and we've collected it in a proper way, how do we analyze that data? And then just as important, and probably more so than even the analysis, is how do we interpret that information? Most of you will probably not be statisticians, and you'll probably not be analyzing a bunch of data, but you will very likely in any kind of professional career be interpreting information that is statistical in nature, and it's very important to be able to do that. So let's look at some examples. This first example is just going to illustrate some of the different terms and some of the different aspects of a study, but mainly just the basic terminology that's so important to what we do in any study. The scenario we're going to look at is this. Suppose we are interested in the average number of calories consumed per day by undergraduate college students in the United States. We select 2,500 undergraduates from across the country, and we collect this information. We've already mentioned the idea of the population. The population in statistics is defined as the group of interest, the group we want to make some statement about. I always think of the population as it's the group that we desire some knowledge about. It's defined in terms of our desire for knowledge. So the group of interest here is undergraduate college students in the United States. That's the group we want to be able to make some statement about. So that's how we define our population. And anytime you do a study, it's really what you start with. So in most cases, it's not reasonable to actually collect data from the whole population, because in statistics, we usually deal with really large populations, and it's very expensive to collect data from everyone. And even if you tried, it wouldn't be very reasonable. From a business point of view, it's never going to be worth the cost. So all those things come into play. And almost always we end up taking a sample. And a sample is nothing more than a subset of the population. So in this case, we already said we're not going to collect data from the whole population. Instead, we're going to select these 2,500 undergraduates. These 2,500 undergraduate students that we select, that is our sample. That is our subset of our population that we're actually going to collect data from. The variable is what you're going to measure. So just like in an algebra class, you think of a variable as something that can change. We call our variables in statistics x, just like you do in algebra whenever we do things mathematically, and you'll see that in here later on. A variable in statistics is the same thing, only now we're actually going to collect this information, and this information is going to vary from individual to individual. So in this case, we're collecting the number of calories consumed, so that is our variable. This is going to change from individual to individual within our study. The data, of course, is nothing more than just that list of outcomes that we collect from our sample. And the individuals, I've already used that term, but that is just each student that's actually involved in the study. So those are the common terms that we use. We call the people in the study the individuals. The list of outcomes, that is, of course, our data, which I'm sure most of you probably already know. A parameter. So whenever we do inferential statistics, it's very important that you understand the idea of a parameter and a statistic. These two terms go together. A parameter is essentially a numerical characteristic of a population, and a statistic is a numerical characteristic of a sample. So the parameter is whatever value from that population that we're actually interested in. So it's going to be one single value. We could be interested in multiple parameters, but each parameter is just a single value. In this case, you'll notice that we're interested in the average. So that average number of calories consumed, that is our parameter. Now, the only way to actually know this value would be to actually collect data from everyone. And of course, we're not going to do that. We're not going to collect data from everyone. So in inferential statistics, the parameter is actually an unknown value. You don't really know what that value is. The whole goal of this study is to estimate that parameter. Parameter always goes with population. That's pretty easy to keep that straight. Basically, the P's go together. Parameter goes with population. The corresponding term from the sample is what we call a statistic. So a statistic is a numerical characteristic of the sample. And just like with parameter goes with population, statistic goes with sample. So keep the P's together, keep the S's together, and you'll keep those straight. So the statistic is something that we're going to calculate. So we're going to take these 2,500 people, and we are going to collect how many calories per day these students consume. And then from that information, we can actually calculate the average number of calories for our sample. So notice the parameter and the statistic are really similar in terms of a study. It's only the parameter goes with the population. It's the average number of calories consumed for the population in this case. And the statistic goes with the sample. In this case, it's the average number of calories consumed for our sample. Ultimately, what we do is we use our statistic to estimate our parameter. And of course, we know there's error in that process, but that's the way this process works. So like if you think about the president's approval rating, whenever you see that 40% plus or minus 3%, that 40%, that is our statistic. That is the value that is calculated from our sample. We use that to estimate what the value would be for the population, which of course is the parameter. This process of using these 2,500 undergraduate students to estimate all students in the U.S., this does fall in the branch of inferential statistics, which we've already talked about. Anytime you're making an estimate, you're taking a sample and making an estimate about a population, that is the branch of inferential statistics. And of course, there is error involved in this process, and we've already mentioned this as well. There's error because we didn't collect data from the entire population. The whole point of this is to estimate, right? And when you go to estimate something, that estimation process is going to include error. So there's always error in inferential statistics because we don't have all the information. We're trying to estimate information that we really don't have. And there are ways to do this really well, but they do involve error. We have mentioned the idea of, instead of collecting data from the 2,500 undergraduates, what happens if you collect data from all undergraduates in the U.S.? Well, if you do that, that is what we call a census. You don't see these very often. Every 10 years, the U.S. does a census. Of course, it's not perfect, but the U.S. Census is the one place where you do see a really big population and a census being used. Businesses are never going to use a census because it's just a very expensive process and it's never going to be worth the money. The only other time that you'll sometimes see a census is you will see a census sometimes in situations where you have like a specialized population, like you only have a population of like 100 people. If your population is 100 people, then maybe you collect data from all those individuals rather than taking a sample. But for the most part, we don't use a census because it's a really expensive process. If you do go through this process of collecting data from all undergraduates in the U.S. and you summarize that information, then of course that does fall under the branch of descriptive statistics, because now, as long as your measurements are accurate, there is no error. So the key caveat to that is there error involved in this process. Whenever I talk about error, I'm talking in this case about statistical error from the statistical process of summarizing that information. Now, we're going to assume that we're actually measuring things correctly, and that is something else that we'll talk about in this first unit later on, is the idea of how accurate are our measurements. Because, of course, if you don't measure something accurately, then you get measurement error. But that's not what I'm talking about here. I'm really talking about error from the statistical process. And when you simply describe the data you have, as long as that data is good data, then there is no error in that process. So if you truly did a census and you did descriptive statistics, there would be no error. Now, commonly, we do use descriptive statistics, but we don't typically use them on a census because a census is not very common. What we do a lot of times, though, is we take a sample and we describe the sample. And this is one of the things that this is what we do in Unit 2. We really talk about how we describe a sample. So when you describe a sample, you do have to be careful. You don't want to make conclusions about the population based on information you collect in a sample. But what you can say is, for this sample, we found this. And this is very useful information, because we can say for this group of people that we sampled, this is what we found. And even more importantly, once we describe that sample, then we can start moving on to the idea of inferential statistics and use those descriptive statistics to start to estimate the population and deal with error. So you have to understand descriptive statistics first, and then we talk a lot about probability, because you have to understand how the probability works when you go to estimate something. And then we start to talk about inferential statistics, which is how those descriptive statistics along with probability allow us to start to make conclusions about the population. The other thing that I just want to mention one more time, and I've kind of already mentioned this, is it realistic to collect data from all undergraduate students in the U.S.? And the answer to this is, of course, no. It's a very difficult thing to do. And even if you could do it, it would be very expensive. So it's almost never going to be worth going through this process of collecting data from an entire population, unless it's a small population. It's just not a very common practice. Instead, what we typically do is we take a sample, we describe that sample, and then if we're interested in the population, we estimate the population through inferential statistics techniques. So those are important. It's very important that you understand these terms. There's lots of things in here that you don't have to memorize. You can always look things up. But things like sample, population, statistic, parameter, those are things you just kind of have to know, because I will use those terms over and over again as I present material, and it'll be much harder to follow if you don't know what those things are, because those are just key to any study in terms of how we set things up. So that's kind of the first thing that we do in this first section, is just make sure you get those terms down. That idea of a sample, population, parameter, statistic, variable. Make sure you can look at a scenario and you know what those things are. Let's talk about some different kinds of studies. There are three main kinds of studies that we deal with. Those are observational studies, simulations, and experiments. So observational studies, you can pretty much get that from the term itself. It's just simply when we observe. We're not trying to influence the responses. The difference between an observational study and an experiment is in an experiment we actually impose something on the subjects. The whole purpose of an experiment is to measure whatever you impose on the subject. So observation, you're not imposing anything, you're just observing. Experiment, you're imposing something and measuring the effect of what we impose. A simulation, simulations are when we simulate an actual experiment where we don't actually do it, and sometimes there's situations where that's beneficial and important, especially when we're going to put life in danger. That's the main time you see simulations, like you see car crash simulations. Obviously, you're not going to do an experiment because that would mean you had to put people in cars and crash them. So instead, what we do is a simulation. We simulate those circumstances, and we measure the effect on the dummies in the car rather than actual people. That's the idea of a simulation. So one of the main things you have to be able to do up front here is, just given a scenario, is just to be able to identify what kind of study it is. So here's the first one. Suppose that we send out a survey to 1,000 individuals asking about their consumption of fast food. An example item might be, how many times per week do you typically eat fast food? So surveys are very common. Surveys are probably the most common way that you see data collected these days. And the main reason for that is because surveys are really, really cheap. And because they're cheap, it's a cheap way to get data. Because they're cheap, they're common. However, their data is not usually the best. Experimental data is way better than observational data. And when you do a survey, surveys are typically not trying to influence the responses. They're just trying to collect information. And that's what's done here. How many times per week do you typically eat fast food? We're not trying to impose anything. We're just interested in collecting information or observing. So surveys are observational studies. And as we talk about observational studies, we do spend a good amount of time talking about surveys because those are the most common. When we talk about observational studies, surveys is really the focus, and we spend a good bit of time talking about the idea of a survey. Here's our second example. I don't know if you've seen the show Mythbusters, but it's got lots of these kinds of scenarios, so it's a good show to see some people test stuff. It's an older show now, but there still are reruns on TV sometimes. On Mythbusters, they once tested to see if it was possible to kill someone by dropping a penny from the highest of heights. So these are the scenarios where you're definitely going to impose something on the subject because you're going to drop a penny and see if it kills them. Obviously, this is a case where you're not going to do an experiment because you are not going to drop pennies on people's heads and see if it kills them. So instead, what you do in these cases is a simulation. And these are the kinds of scenarios where you see simulations. Simulations are typically done when you're going to put life in danger. We'd prefer not to do simulations because simulations are way more expensive to conduct. It's way easier to use actual people to conduct a study rather than try to simulate the effect. The computer and manpower that goes into doing something like a car crash simulation is just a very, very expensive process. But in cases like this, where you're going to put human life in danger, of course, a simulation is the proper choice. Here is our third example, and you could probably guess this by process of elimination. Suppose that a study is designed to compare teaching methods. Specifically, we want to see if students learn introductory statistics better through an activity-based approach or a more traditional lecture approach. Students will be assigned to one of the teaching methods, and the results will be measured based on the final exam. So this is an experiment. You're imposing something on the subjects. You are specifically imposing the teaching method. You are controlling that. The nice thing about an experiment as compared to an observational study is you actually have control over what you're imposing. So here we are going to choose who gets the traditional lecture approach and who gets the activity-based approach. You don't get to do that in an observational study. In an observational study, all you can do is observe these variables and then look at people within those categories. But with an experiment, you can actually put people within those categories, and because of that, you're able to make way stronger conclusions in an experiment than an observational study. You've seen the idea of subjects before, I'm sure, but the subjects in an experiment are just the people or the items, whatever you're testing in the experiment. So in this case, that is the students. Whenever we talk about a treatment in an experiment, whether the treatment be positive or negative, electric shock is still called a treatment if that is what you're imposing on the subjects. Whatever we're imposing is known as our treatment. So our treatment in this case, of course, is the teaching method. And in this case, there are two different teaching methods. So that means we have two treatment groups. So this is a pretty simple experiment where we just have basically two teaching methods and we're going to compare them. Let's look at an experiment that's a little more messy in terms of its treatment, because you can have multiple variables in an experiment. So let's look at one that has multiple variables. In this class, we don't do anything beyond just a single variable or two variables. We don't do anything beyond two variables, but if you give a 50-question survey, then technically you have 50 variables. In a higher level stats class, that's something that you might look at. You might look at, well, what happens when we start to expand this out and we have more and more variables, and things do get more complicated as you get more variables. So here's this scenario. Suppose that we conduct a study looking at how diet and exercise affect a person's cholesterol level. For the diet variable, we will have three types: Atkins diet, South Beach diet, and Weight Watchers. And for the exercise variable, we will have three categories: walking, jogging, and biking. So whenever you have more than one variable here, because now we have diet and exercise, so we have to look at how many treatment combinations we have. So obviously for diet, we have three different kinds of diet, and for exercise, we have three different types of exercise. So in order to get the total number of treatment combinations, it's a multiplicative relationship. You always multiply. So we have 3 times 3, or 9 treatment groups. With these treatment combinations, this can get really messy really fast, which is why you tend to not see a bunch of variables or a bunch of treatment groups, because 9 treatment combinations is quite a bit. But if you add another variable that has 3 categories, then you're up to 3 times 3 times 3, which is 27 different treatment groups. So if you start adding too many variables or too many treatment groups, then you can really end up with a messy experiment. So it's something to always be cautious of. It's best not to have too many treatment combinations unless you really want to spend a bunch of time and money on a given study. One of the things that we commonly do with these kinds of studies where we have more than one treatment group is we identify the different treatment combinations as we look at them. There's a couple ways to do this, but the common way, especially when you have two variables, here diet and exercise, is to simply create what we call a treatment diagram. And basically it's just a table, and it will represent the 9 treatment groups. So you just let the rows of the table represent one variable, so in this case diet, and you let the columns of the table represent the other variable, in this case exercise. And the cells within this table, of course, represent the 9 treatment groups. So you can see that there are 9 treatment groups. Treatment group 1 would walk and do the Atkins diet. Treatment group 2 would jog and do the Atkins diet, and so on. You have to have individuals in every one of these treatment groups when you go to conduct a study. So this treatment diagram is a good way to look at what all your treatment combinations are, especially when you have 2 variables. So those are your types of studies. We have one more thing to talk about, and that is how we classify variables. So there are 2 different ways to classify variables. We classify variables based on their type, and then we also classify variables based on their level of measure. So we'll start with type. So there are 2 types of variables. So when you hear you hear or you see a question that says what type, there's 2 types. It's either qualitative or quantitative. Those are your 2 types. Qualitative data is essentially non-numerical data. Quantitative data is numerical data. You do have to be a little careful with my definition of qualitative data being non-numerical. By non-numerical, we really mean in statistics that it has no numerical meaning. So every once in a while, you'll see a number that's just used as an identifier, but there's no mathematical meaning to that number. And if there's no mathematical meaning to it, then that means that it's still a qualitative variable. If you do have a quantitative variable, we subdivide those up into either discrete or continuous. Discrete, from a basic standpoint, is something that you count. Continuous is something that you measure. So essentially discrete is something that has outcomes that are like 0, 1, 2, 3, 4, and so on. But the key thing is the outcomes are specific points along the real number line. Like how many kids someone has. You're going to have 0, 1, 2, 3, 4, and so on. You're not going to have 1.5 because you can't. It's not a continuous scale. A continuous scale means you can break it down. So if you measure something like weight, well, you can have 1/2 pound, 1/4 of a pound, an eighth of a pound, and you can continuously break down that scale. So it's just like a continuous variable in algebra, where you have a continuous function, where you have basically an infinite number of points between any 2 points on the real number line. That's the idea of a continuous variable. And the way that we deal with these variables, discrete and continuous variables, in terms of probability is different. And that's why it's very important to distinguish between the different types of variables, and if it is quantitative, whether or not it is discrete or continuous. So for now, the big thing we need to be able to do is, if you're given a variable, you need to be able to identify it by its type. So here's the first one. Number of hot dogs sold at a Cincinnati Reds game. So it's obviously a number, so that makes it quantitative. And in terms of sales, they're going to sell 0, 1, 2, 3. It's going to be something that they count. So that is going to be a quantitative variable, and it is going to be discrete. Religious preference. Well, religious preference is simple, because if you think about the outcomes are not numerical. Anytime you have an outcome that is not numerical, then it's obviously a qualitative variable. These are ones to be careful of. Student ID number. Student ID number is technically a number, but when you think about that number has no mathematical meaning. You're not going to perform a mathematical operation on a student ID number. It makes no sense to do so. If you add two students' ID numbers together, it means nothing. So there is no meaningful quantity there, which means it is still a qualitative variable. So it's something to be aware of. Anytime you use a number as just a label, it's still not numerical. Just because it's a number doesn't make it numerical. It's got to mean something numerically in order to be a quantitative variable. So something like student ID number is a qualitative variable. A person's weight, that is obviously a numerical value. It has meaning. And it is something that you measure, so that is a continuous quantitative variable. The way I like to think about continuous variables is just think about, well, you think about whether it's measured, but think about, can you break it down? Can you have half of a pound, a fourth of a pound, an eighth of a pound? And obviously you can, which allows you to know that this is a continuous quantitative variable. Number of students in a class, once again, that is numerical. That one is something that you're going to count. You're going to get 0, 1, 2, 3, 4, and so on. Temperature outside in Fahrenheit, again, that is something that you measure. So that is going to be quantitative. It is continuous. You can have half of a degree, a fourth of a degree. When you measure something, you can continuously break down that scale. So that's your first classification. Your first classification is in terms of the type of variable. The other way that we classify variables is in terms of their levels of measure. So there are actually 4 levels of measure. The levels of measure are nominal, ordinal, interval, and ratio. Nominal is considered the lowest level and ratio the highest level. And basically, as you move up through the levels, you are adding a characteristic every time you move to the next level. So the way it works is nominal really, nominal has no implied criteria. Nominal is just an identifier. When you move to ordinal, there becomes an order to the outcomes. When you move to interval, there becomes meaningful differences between the outcomes. And when you move to ratio, there is meaningful ratios between the outcomes. And that's basically the way this works. What I highly recommend you do as you identify levels of measure is I highly recommend that before you worry about a level of measure, you always start with, is it qualitative or quantitative? Most qualitative variables are nominal, and most quantitative variables are ratio. So almost all variables that we deal with are either nominal or ratio. They almost all fit into one of those two categories. Nominal is most qualitative data. Ratio is most quantitative data. But we do have these two categories in the middle that we have to deal with. Ordinal just means there's some sort of order, but you don't have meaningful differences. So something like any kind of ranking. So like ranking of college football teams. We know who's first and who's second, but we don't actually have a difference between first and second. Like we have a meaningful order, but we don't have a meaningful difference. Interval is actually the toughest one. Interval has to be quantitative because it has meaningful differences, but it does not have meaningful ratios. The common scenario here is temperature in Fahrenheit. So that's the example that I'll explain this with. And this is the hardest one. Temperature in Fahrenheit is an interval level of measure. So one way to think about this is think about, just compare two temperatures. Like suppose it is 40 degrees in Lexington today, and suppose it is 80 degrees in Orlando, Florida today. If we compare 40 degrees to 80 degrees, and we do that comparison, well, if we take 80 degrees minus 40, that will give us 40 degrees. And it is reasonable to say that it is 40 degrees warmer in Orlando than it is in Lexington. That is a meaningful ratio, or a meaningful difference, I'm sorry. That is a meaningful difference. 80 degrees is 40 degrees warmer than 40 degrees. We subtract those, that is meaningful. However, if we divide those, it is not meaningful. You can take 80 divided by 40 and get 2, but what you can't do is you can't say it's twice as warm in Orlando as it is in Lexington. That doesn't make sense. It doesn't make sense to say it's twice as warm. Now, ultimately, the reason why that ratio doesn't make sense is because temperature in Fahrenheit does not have what we call an intrinsic zero value. So in most variables, the zero value means there is none of that quantity. That's what an intrinsic zero value means. It means that there is none of whatever quantity you're talking about. So like someone's weight. If there's a weight of 0, that means there is no weight. There's none of that quantity. So it has an intrinsic zero value. But if you think about temperature and you think about 0, 0 does not mean there is no temperature. 0 is just another measure of temperature. And because it does not have that 0, that intrinsic zero values, the differences are meaningful and the ratios are not. And that's the hard one. That's the one you really got to be careful about. There's very, very few variables that fall into the interval category, but there are a few that are quantitative variables but don't have that intrinsic zero value, which means they have meaningful differences and not meaningful ratios. Let's do a few of these. We'll start out with the hard one. Year of high school graduation. So if someone graduates in 2010, someone else in 2020, that is a 10-year difference. That difference is meaningful, so that is a meaningful difference. This is a quantitative variable, so I always recommend that with quantitative variables, you kind of start at the ratio interval end, and with qualitative variables, you start at the nominal ordinal end of the scale. So this does have a meaningful difference. However, you can't divide 2 years and say that is meaningful, because once again, if you go back to that 0 value, the year 0 is not an intrinsic zero value. It doesn't mean there was none of that quantity. There was no year. That doesn't make any sense. So this is actually the difficult one, which is that idea of an interval level of measure. Rank of students in a graduating class. Well, honestly, if you read the first word and it says rank, that will tell you there is an order. But if it's only a rank and there's not differences between the two, then that is what an ordinal level of measure is. An ordinal level is always that scenario where you have a relative comparison. You know who's first, second, third, but you don't have meaningful differences between those outcomes. So anytime you have a ranking, it's going to fall into that ordinal category. The number of hot dogs sold at a Legends game. So that is a quantitative variable. So anytime you have a quantitative variable, I really recommend you start with the ratio level. And if you think about, is this ratio? Well, is 100 hot dogs twice as many as 50? Yes, that ratio is meaningful. If you think about 0 hot dogs, that means no hot dogs. That is an intrinsic zero value. So this is for sure a ratio level of measure. Most quantitative variables are ratio. Because most quantitative variables have meaningful ratios, they have that intrinsic zero value. Religious preference. So that is a qualitative variable. There's no order. So most qualitative variables are nominal. And of course, that's what this one is. This is a nominal level of measure. Student ID number. We already said that was qualitative, which means it's probably nominal. And if you think about, is there any meaningful ordering to those? I mean, you could put them in order, but alphabetic order does not count, and neither does numerical order if it's something like student ID number. That is not a meaningful order because the numbers themselves don't mean anything. So this is just a nominal level of measure. Nominal levels just means it's an identifier. A person's weight, that is ratio. 200 pounds is twice as much as 100 pounds. 0 is an intrinsic zero. It means no weight. Number of students in a class, that one is also ratio. Ratio is when you have meaningful ratios. 50 students is twice as many as 25. 0 means no students. So that is a meaningful ratio. So those are the big things in this first section. The big things is the basic terminology and how we set things up. Then the different types of studies, and then the classification of these variables. So this is kind of the basics of a lot of what we're going to need as we move forward in terms of classifying things and in terms of just talking about different kinds of studies. So it's very important that you get comfortable with this information. That is the end of section 1A.